Hi, everyone. Good morning. Welcome back to BIEB 152, Evolution of Infectious Disease. This is lecture number 14. Today, we're going to go over a class of epidemiological models called SIR models. A lot of the predictions that are forecasting different dynamics of SARS-CoV-2 are based on SIR models. So I think that this lecture will be really helpful in understanding, a lot of things that are in the news and what epidemiologists are telling us, and understanding why social distancing is so important. So we are also going to use those models in the framework to understand a little bit about why viruses sometimes evolve to be more virulent or less virulent, or I should say not just viruses, but pathogens in general. Okay, before we get to all of that, let's of course do taking the temperature. Okay, so we've looked at this graph so many times. I always sort of go back to it just to see what's going on in the country and whether or not we're in a better trend. And we can see that since April, it appears that we have sort of leveled off and maybe even we're declining in the number of cases. If you look at this graph, one thing that really jumps out at you are these cycles of ups and downs in the data. They have a periodicity of 7 days. And so I think that that's probably because reporting is not uniform across all the days of the week. Maybe there's a little bit of a delay on Saturday and Sunday or Monday, and that gives you that sort of up and down appearance. So really, if you want to get a sense of the trend, it's not that the disease is being very erratic. This is a 7-day average of those bars. And so this pattern is much more indicative of what's going on in with the dynamics of the disease. So we see overall the number of cases, or new cases, I should say, are declining over time in the United States. That's really positive. That's really good. And so the question is, a lot of times we've talked in the lecture about how social distancing is so important, and we see the number of cases continuing to decline, but we know that if we look at cell phone data from April and cell phone data from May, we know that people were social distancing in April, they were staying at home a lot more, and then people became much more active in May. This is in states that relieved their populations from sheltering in place, and in states that advised people to shelter in place and to not open businesses and so forth. So the question is, if people are moving around more, what's going on? Shouldn't we see an uptick in the disease? And so I think that there's probably two explanations for why the disease isn't going back up. And there's probably many, many more explanations. One that I didn't include here is that maybe people are leaving their homes more often, but they're being very careful when they're out in public, that we've all learned our lesson about keeping 6 feet away from each other, not going to crowded places, and washing our hands and so forth. So that's probably one reason. But the other two reasons I want to focus on is that New York City was driving the major pattern in this graph early on in the dynamics. And it's driving, and now we know that New York City is also dropping down. And so it's driving a lot of this pattern where it looks like the number of new cases is decreasing over time nationally. Actually, underlying that is mostly based on New York City. If we took out the effect of New York, we'd see sort of more of a plateau. And so what's happening in New York City is, of course, people are traumatized, and so they're being very careful. But people are starting to come out more and more in New York City as well. And we're going to talk about this phenomenon later in the lecture called herd immunity. We discussed it once early in checking the temperature of COVID-19 section, where it's this idea that once a population has a large number of immune people or resistant people or recovered people, those are going to be synonyms in today's lecture. So people that had the disease, recovered, and now are immune to the disease, once you have a lot of those people in a population, then the disease has a harder time to spread. Basically, you can think of these people as kind of speed bumps for the disease. if a particle lands on that person, it can't infect them because they have immunity to that pathogen, so to SARS-CoV-2. And so you might be wondering, you might have heard news that it's unclear whether or not people actually develop immunity to SARS-CoV-2 and how long that immunity actually lasts. So this has been in question basically because this is a new disease and we just are kind of in a fog of understanding it. But there is more and more research coming out. I'm trying to, with the goal of understanding SARS-CoV-2. And there is a paper that's talked about here. This is an article from Science. And what they found is that there are T cells in COVID-19 patients that confer immunity, and the types of cells are ones that should confer long-lasting immunity to COVID-19. And so it does appear that people, once they are infected, become immune, and they're going to maintain that immunity for a long time. That's really good news. That's good news for vaccines. That's good news for just reducing the spread of SARS-CoV-2. Even if we don't have a vaccine, all of these immune people are going to be these sort of speed bumps for the progress of the disease. Okay, so we'll get back into herd immunity later. So that's what's driving, that's part of the explanation probably for why New York City is dropping down so much, is that something like 18% of the people in New York are recovered from the disease, and so the SARS-CoV-2 is just having a harder time spreading. But what else I think is probably happening in this data, so even if you remove New York City from this larger pool of data, you still see that there's many states where people are not social distancing as much as they did before, but the numbers are beginning to decline. And we have talked about this before, how there might be a possible seasonal effect on SARS-CoV-2. So certainly other coronaviruses are sensitive to the summer. They don't spread as well to the summer. We don't know for sure if SARS-CoV-2 is also impacted by summer conditions. And great epidemiologists predicted a month ago that they might not be affected by summer conditions. However, I think the data are beginning to shine a light on the fact that it probably is affected by summer conditions. And the way that summer conditions work is that the increased humidity in the air reduces the potential for viral particles to aerolize. And aerolized particles can spread really broadly. They can stay in the air for a very long time. They can spread over large distances. And so this, if a viral particle is able to achieve this, then it can spread very quickly. There is not great evidence yet that SARS-CoV-2 aerosolizes, but very similar viruses do aerosolize, and there's no reason that I can see that this would be a unique virus that wouldn't be able to do it. And given how fast this disease has spread around the globe, it seems likely that it does have this mode of transmission. So in the summertime, there's more humidity, less aerosolized particles. And so this is the effect of, if we have social distancing of 6 feet, this is a similar effect to that. Or if we wear a mask, those particles are less likely to spread. So all of these things, you can think of the air with humidity as buffering the spread of the disease a little bit, having some effect similar to a mask or similar to social distancing. And the other thing is that in warmer temperatures, viruses spontaneously decay much faster. So viruses, they have a lifespan. They don't stay forever on surfaces. They decay on surfaces. They decay in the air. And so if you add UV radiation from sunlight, if you add heat, they're much more likely to decay faster and faster. And so all of these together, these what we call abiotic environmental conditions, are probably slowing down the spread of the disease in the summer. And so hopefully we do have some relief from this pathogen in the summer. So I'm not giving you guys a license to just go out because, hey, we have relief, it's warm, it's humid out, blah, blah, blah. No, you should continue doing what you're doing. These are all just layers of things that reduce the rate of the spread of the disease, but people are still going to be transmitting the disease. And so you should still keep social distancing. You should keep that mask on. What we're doing is we're layering on all of these different protective agents so that the rate of transmission from one person to another person is really, really, really low. So, we will have hopefully a relief in the summer, but this thing is going to be, it's everywhere in the United States, and we need to be aware of it, and we need to take precautions. So how I see this playing out, I think the best case scenario in the next 6 months, and it's a hopeful one, but I don't think it's irrational, is that we're going to have some relief from this disease in the summertime. Not as many people will be sick, the prevalence of the disease will be lower, and we can leave our houses more often, be outside, not crammed into closed-in places inside, but leaving our houses slightly more than we are now. Then comes the fall, and the conditions change back to where the disease is going to spread. And hopefully in the fall, we have a number of things accomplished. So we've stockpiled our PPE. We've gathered more tests so that we can more efficiently or more pervasively test people. And we can track the disease and keep better control of it. So hopefully we achieve those things. Maybe some therapies are more widespread. Remdesivir seems promising, and maybe there's other therapies as well. And also, hopefully, not by the fall. That seems unrealistic. But hopefully, in late winter, maybe even, or soon after that, we actually get a vaccine. And so we talked about the Oxford group and how they're developing a vaccine and are very far along in progress. They're starting a very large-scale study with lots and lots of patients taking the vaccine. And so there's other good news on the vaccine front in that in the United States and Massachusetts, this company, Moderna, had a very successful small-scale study, so just 8 people. So they're still at an earlier step than the Oxford people, but their results are really compelling. There's no alarming side effects yet, just in this small population of 8. Of course, when you scale up, you can uncover more side effects. But what they found is that there are antibodies in these patients against COVID-19 that are at levels above or equal to people that have already recovered from COVID-19. So it appears, just by this one measure, that the vaccine is triggering the same immune response as the natural disease does. And so this is really hopeful news. It's great to see that there's sort of multiple different types of vaccines and multiple different companies producing, or companies or schools or governments producing these vaccines. And so we're kind of hedging our bets here, and hopefully not just one, but multiple of them pan out. And so we can distribute them more broadly. And if there's sort of trade-offs for using one or the other, we can optimize those trade-offs and strategize which population should get which types of vaccines. So this is really good news. And I am hopeful that we will have a little bit of a relief in the summertime, and then coming into the fall, we'll have our technology up and ready and our supplies up and ready to combat this disease. But life is not going to be normal, or maybe never again, but certainly not anything like what we used to experience until we have this vaccine. Okay, so let's actually get into the lecture. And so a lot of the parts of the taking the temperature today are actually interlaced with throughout this lecture, because now we're really getting to the mathematics of pandemics, or the mathematics of the spread of infectious diseases, and also the mathematics underlying why natural selection sometimes pushes pathogens to be more virulent or less virulent. So those are the 2 questions that we're going to answer today. Why do some pathogens spread and others do not? So, the original SARS, the original MERS, their coronavirus is very similar to SARS-CoV-2. but they didn't spread as widely as SARS-CoV-2. So why is that? It can just be happenstance, but there might be characteristics of the viruses too that determine whether or not they spread. And then the second question is, why are some pathogens virulent and others are not? And so we know that MERS and SARS were much more virulent than SARS-CoV-2. We know that Ebola is extremely virulent. We know that the common cold, other coronaviruses, are not as virulent. And so what is determining, not just at a mechanistic level, but at an evolutionary level, what sort of shapes the direction or determines the direction in which evolution goes? Why does it push some viruses to be really pathogenic and other viruses to be benign? Okay, so there's basically one class of mathematical models that really give us some insight into these two questions. Okay, so we're going to dive straight. It is 8 a.m. and I just threw a bunch of equations at you. So we're going to dive straight into these equations. Do not be nervous about the math. Yes, these are differential equations. You might have not have seen differential equations since, I don't know, since high school or maybe physics class. I want you to sort of be able to look at these equations and read these equations, but we're not actually going to use these equations to make any calculations. These equations just help you understand what variables determine the spread of diseases. And they're your sort of first inroads and understanding epidemiological models. And so don't freak out. I'm going to walk you through how these guys work. And I hope it builds some kind of intuition for how diseases actually spread. Okay, so what the model does is, so these are differential equations. They are keeping tracks of the rate of change in populations. And these are sort of population level models. So it's modeling humans and the number of humans that fit into three different categories: susceptible, infected, or recovered/resistant. I'll probably flip back between recovered and resistant, or even immune. That's what the last category is. This is a model that's not keeping count of the number of viral particles in a person or in the environment or how they're spreading around. What it's doing is it's keeping track of the number of people that fit into these three different categories. And so let's start with the dsdt is the rate of change in the number of susceptible people. didt is the rate of change of the number of infected people. And drdt is the rate of change in the number of resistant or recovered people. Okay? So there are a number of variables that determine the rate of change of the number of susceptible people, infected people, and recovered people. Here are the variables, and in the next step, we'll go over how you put these variables together to actually give you those rates of change. And so the first one is beta, infection rate. This is the transmissibility of a disease. The probability of a pathogen will spread from an infected person to a susceptible person. So that makes sense. How infectious a disease is determines the rate of change from a susceptible person to an infected person. Virulence, death rate imposed by the disease. So if you're killing off a lot of infected people, that's going to obviously influence the number of infected people in the population and therefore the rate of change of that population. D is just natural death rate. This, in a lot of models, is not important if they're run over a short time span. But sometimes you're modeling diseases like HIV that have chronic infections for the lifetime of patients, and that lifetime can be years to decades. And so you do need to start incorporating death rate. This is just natural death rate, not caused by the disease. Virulence is the death caused by the disease. This is just the natural death rate in the population. Okay, recovery rate. Recovery rate is 1 divided by the infection duration. And so this is how fast does a person heal? Do they recover from the disease, and do they become immune to the disease? So faster recovery rate, better for the patient, and faster that you're going to get infected people turning into resistant people, I turning into R. Reproductive rate. Now, this is very similar to this D, and often this is not included in models, but sometimes it is. And this is the rate at which a population is just growing for natural reasons. So from birth or from immigration into an area, all of those different population processes. So how fast would a human population grow without death is how you get to R. Okay, so these are all the different variables. Definitely go back over them in your notes and really understand what they are. And now let's walk through how to stepwise build these variables up to give us these rates so that we can determine, how many sensitive people will there be at a certain time in a population? How does that change over time? How many I's will there be? How many R's will there be? So forth. And so what I'm going to do now is we're just going to sort of walk through. So the rate of change of the number of susceptible people in the population is going to equal 3 different modules of variables. And the way that when I look at these models, I break them down are modules or compartments that increase the population size and compartments that decrease the population size. And so what's happening here is that there's a growth rate, and that is a growth rate, and you're going to apply that to the number of susceptible people. And so, if you have one person reproducing, well, you're not going to get as many babies in the future. But if you have 100 people reproducing, then you're going to get more babies in the future. Even if you have the exact same rate of growth, it's just you have more people being able to produce babies. And so that's why we have RS here. And then let's break it down into the things that remove people, the processes that remove people from this susceptible category and put them into other categories, remove them from susceptible, sometimes put them into I, or just they die out. Okay, so let's go into this one here. And so what we have is beta, that's the infection rate. That's the rate at which when a susceptible person encounters an infected person, the disease spreads from that infected person to that susceptible person. And so this module here determines how many people turn from susceptible into infected. This makes sense, right? So we have an underlying rate that disease is spread. And so if you have tons and tons of S's and very few I's, well, that disease is going to be a little bit slower to spread at first because there's not that many infected people to spread to S's. As if the opposite were true, where you have tons of infected people and very few susceptible people, well, this rate would slow down because you wouldn't have as many receptive people for the disease, and so it just wouldn't spread as well. So if you have lots of susceptible people and lots of infected people and a high beta, then that disease can sort of spread like wildfire and have a really large rate of increase per unit time, per day or whatever. Okay, and then what this is this is just a death rate. This is analogous to the reproductive rate. This is a death rate where the death rate modifies the number of S's, so susceptible people in the population. This is just sort of normal population dynamic stuff. People naturally have a mortality rate. So these are called coupled differential equations because you can see that they're interrelated with each other. So the way that you get more infected people is that you get people getting infected, so leaving this category and moving to this category here. And then we also have a series of ways that people leave this infected category. And so the first is just the sort of natural death rate. This is the exact same rate as for susceptible people. This is not the enhanced death caused by virulence. This is the enhanced death caused by having the actual disease. So if the pathogen does cause mortality at a certain rate, it's determined here, and this is what when we say that people died from COVID-19, it's this compartment here that determines that. And now we have a new compartment, and this is recovery, right? So most people for COVID-19 don't die. Most people actually do recover. And so that recovery rate means that they were infected, but they're no longer infected. And so this here is turned into or translated into this new population of recovered people. And so this is just the rate of recovery times the number of people that are infected. And so over time, the number of R's builds up. Of course, also in this equation, we have to account for the natural death rate of recovered people as well. Yes, they're immune to the virus now, but they can still, experience some other sources of mortality. Okay, so that is sort of walking through how these models work, how they're organized and why they make sense. And now what we can do is we can actually use these models to predict population dynamics. And that is what helps us understand, how fast will this disease spread? What kind of measures can we take to reduce the spread of the disease? How can we make predictions out into the future for disease dynamics? Before we get into that, I just want to show you this picture. Sometimes looking at equations can be confusing and even triggering. Students can feel a lot of stress looking at all of those variables. And so here is just a cartoon version of that mathematical model. And even when you read scientific papers that publish these types of models, often they'll publish this diagram, just because even scientists that are trained in reading coupled differential equations, they find it easier to see how the equations work just by this sort of picture diagram. And so this is called a compartmental model, where we have the total number of susceptible people, we have a fraction of them dying off, and we have a fraction of them that are moving into this infected category, and that's determined by both of their population densities, but also by the beta. So how infectious the agent is, how likely it is to spread from infected to susceptible, causing more infected people. Then you have death, natural death in this population, and death from the actual virus or the pathogen. And then you have a rate at which these infected people are recovering and turning into the recovered population. And of course, they have a natural death rate as well. So a couple more things before we get into the actual model predictions. This is a mathematical model, and all mathematical models make what we call simplifying assumptions, right? So when we make you should think of a mathematical model as like a map of biological processes. And so when you build a map, right, you don't put every little detail into that map. You simplify it, you focus on the streets. If you need to navigate, you focus on the contours of the hills if you're hiking. You have a globe where you're focusing not on streets or hills, but on the relationship between where different countries are on Earth. And so all of these maps are these simplifications. And you wouldn't make a map that was identical to the Earth. That would just be the Earth. You wouldn't make a map that's identical to the campus. for that level of detail, it would have to be as big as the campus. And so we make these maps as simplifications to help guide us. And that is what a mathematical model does as well. It makes assumptions, hopefully that don't interfere with its predictability, but these assumptions are sort of necessary to sort of simplify things so we can understand them, so we have this map, and so that we can make hopefully accurate predictions as well. Okay, but some of these assumptions can violate important principles of the diseases that we're trying to model. And if those violations will impact, it can impact the predictability of the model, and so it can be problematic. And so in this model, this is a very simple SIR model, but people have made more complex models to better suit the particular pathogens that they're studying. And so some of the simplifying assumptions in this model that pathogens can violate, not all pathogens, but some of them do, is that the recovered are immune and do not gain sensitivity. So that means that once you get into this category here, you never go back and become susceptible. We know that sometimes people do gain sensitivity to diseases, and so this assumption maybe works for some viruses or some pathogens, but not all of them. There's no spatial structure. This is a model where you have a completely well-mixed population where susceptible people are interacting with infected people, but when you add spatial structure, like things like quarantine, that's obviously going to influence the interactions between these two populations, and so it's going to influence their ability to spread. This model does not have that feature embedded in it. The disease does not evolve. So obviously that's important for our class. These variables here are static. Once they're set in the model, they're done. But we know pathogens and other pathogens can evolve and humans can evolve. And so these variables can change over time through evolution or through changes in our behavior. And so that is a simplification that is not like reality and can be problematic. And so there are more complex versions that people have come up with. If you do a quick Google search, you'll see lots of different variations of the SIR model. This is a core structure of the SIR model, but it's not going to be the one that the epidemiologists of today are using to predict SARS-CoV-2. It's going to have the skeleton of it, but not all of the intricacies of the ones that are actually being used to predict the disease. So just to sort of think about these simplifying assumptions and how you would augment the model, there are some pretty easy ways that you can do this. And so if you know that there is some rate that recovered people actually then transition back to susceptible people, there's a model called an SIRS model, where you have this sort of flow to this point, but then you have flow back at a given rate. We'll say maybe that's alpha back to susceptible people. And so you can imagine how you can build in more complexity into these models. Of course, the thing that I'm most interested in is incorporating variables in this model that allow the model to evolve or allow the disease to evolve in the model. And so you could imagine that beta is not a static number, but beta increases over time or changes over time that is consistent with the evolution of the pathogen. Okay, so that's sort of the general framework of the model, and just how models work and how we can build in more complexity and so forth. But now actually let's use that model and start looking at population dynamic predictions from that model. And so this is a model prediction that where we've used a given set of beta, virulence, and recovery rates. And we sort of see this cool dynamic. So let's just sort of start out to describe the model. So what these researchers have done is they start with a population of about 499 susceptible people. they add one infected person to that population, and then they watch the dynamics to see how it plays out. And what we see with this particular pathogen is that it begins to spread from the infected to the susceptible people, causing the number of susceptible people to drop. The reason why this is dropping is that the number of infected people is increasing over time. And as the number of infected people increases over time, then they are beginning to be recovered. And so they then transfer into this third category of recovered. And so this virus is highly, probably has a very high beta. We're seeing really fast, rapid spread. And basically at the end of the simulation, which is just over 60 days. So I should have started out with the x-axis is time, number of days, and the y-axis is number of people. And so the number of people that are susceptible drops to 0, and the number of infected people rises high, but then it begins to drop down because there are now a shortage of susceptible people for the virus to transfer to. And so this drops down, and as that number drops down, the number of recovered increases through time. And so you get this dynamic where basically this virus has entered a population, spread around the population, infected everybody, and now everybody is recovered from the virus. So let's sort of think about different characteristics of these dynamics and how these variables like beta and so forth are would affect the dynamics. And so we see a very steep response here, so very, very rapid decline in the number of susceptible people and a very rapid increase in the number of infected people. And that is indicative of a very high beta. This disease has the capacity to spread very quickly. We see this sort of time lag between the increase of infected people and the increase in the number of recovered people, for this example, is pretty narrow. And so what this tells you is that the recovery time of this is pretty short, and so a very fast recovery rate. And so you can see that these are days. There's just a time lag of a couple days, and so it suggests that the recovery time is just a couple of days, less, maybe a week or a little bit less than a week. And so this is a virus that hits a population hard, spreads very quickly, but people recover pretty quickly as well. And then this is a lot of text, and so let me just sort of walk through what's going on here. So what we see is at the beginning of the trial and the end of the trial, there's basically very, very few people that are no longer in that population. So very few people died. And a lot of these models, especially if they're done on such a short time scale, we're talking months is the time scale for this modeling. People have just assumed that the birth rate and the death rate, the R and the B, so the R and the D counteract each other and are at a steady state. Basically, they're having very little effect, in that the mortality that is caused, or the mortality that's seen in the population, is caused by the pathogen itself. And so since we see that there's lots of people, there's 500 people here and almost 500 people here that are recovered, this indicates that maybe the virus did not completely get to everybody and infect everybody, or it probably actually just indicates that there's been a few people that have died from the disease. But so if you see that the starting population size and the final population size are about the same height, that means that this is not that pathogenic of a pathogen, that it hasn't caused much mortality in the population. If you saw a huge decrease at this point in the simulation, and so the total population size of people was much lower than the initial, then that would indicate that this pathogen is highly, highly virulent. Okay, So let's take a second and look at these different simulations. Here, and we have this question of, what variable did I change when I was simulating this versus simulating this population? So I just changed a single variable, and this was done using this online simulator, this SIR model simulator, which is really helpful and really nice. Of course, in your homework assignment, I'll have you guys look at the simulator and use it. So, okay, let's just take a second. Which variable did I alter? Okay, I altered beta. I think that should be pretty clear based on my description of the steepness of these trajectories in the last graph. So we see very steep trajectory down of susceptible and very steep trajectory up of the I and then also the R. And so everything is just sort of slowed down here. Not as many people are getting infected, not as many people, that's the blue line here. And so fewer people are also becoming resistant, just at a much slower rate. And so the amount that I reduced the beta was actually pretty significant. The beta here is 1/5 of the beta here. So you can imagine that we could be comparing two different viruses that just have different intrinsic betas, or we could be augmenting our behaviors in a way so that the virus has a harder time to spread from one person to another person. And so if we reduced our number of social interactions to 1/5 of what they were before, then we'd actually see this much different dynamic and much less severe spread of the infection. So what this modeling has shown us is this principle of flattening the curve that spread, this concept spread around social media and around the world in the news. And this was our goal with social distancing, was to flatten the curve. And so you have probably seen figures where they show this is what the potential of the disease has, but ideally, we would rather have a pattern which is a lot flatter and lower, where we don't have so many people infected all at once, so that our hospital systems are not overwhelmed, and so there's not just sort of some massive infection and mortality. And so this is showing us that if we reduce that beta, if we reduce the transmissibility of the disease, we could do that through therapies and things like that. But we can also do that just with our behavior, in that we just reduce the number of contacts that we have. So it effectively reduces this beta. So the way that this is working is you're reducing this whole module here. So you're reducing this module, and so you're reducing the total population size, the rate of the increase in the population size of the infected group. And so you're reducing this transfer of susceptible people into infected people. And of course, the way that we can do this with SARS-CoV-2 is that we can do that through social distancing, through hygiene, and I'm hoping that we have this summertime effect, and that these summer conditions are able to reduce the beta, reduce the ability for the virus to go from one person to another person. Okay, so I hope that gives you a better intuition for flattening the curve and how, in a mathematical sense, that slows down the spread of the disease. The other thing that is harder to understand at first is that just changing this one variable beta has this other effect, in that the steady state that this system comes to is different than this system over here. And so over here, what we have are, basically everybody has gotten the disease and everybody is recovered, whereas over here, only less than 50% of the people have gotten the disease and recovered. We see much lower numbers of people not just that we've reduced the spike, but we've actually reduced the overall numbers of people that have been infected by the disease. And that has led us to this sort of new steady state where you have basically 50% of your population are resistant and 50% of your population are sensitive. And so what this model shows us is that by reducing the ability for the disease to spread from one person to another person, you don't just slow it down, but you reduce its ability to penetrate populations. So basically, you can think of as the number of recovered people increase in a population, they create these kind of speed bumps for the disease. They can't spread to those people anymore and then go from those people to the next person. And so overall, the spread of the disease begins to slow down. Well, if you have a disease that has a really high beta, or you're not taking measures to limit the ability for a disease with a high beta to spread, then even if there are speed bumps in the population, it's just going to transmit and spread everywhere, and everybody's going to get sick. However, if you augment your behavior, or if you're dealing with a pathogen that doesn't have a high beta, then you will get the pathogen spreading through the population, but eventually slowing down and stopping when you get to some kind of threshold. In this example, that threshold is 50%. So let's dive into this a little bit more. It's really interesting because you have, more than 50% in this example here, slightly more than 50% of the people remain susceptible. So there's lots of people around that the virus could spread to, but we see that the virus is no longer infecting new people, and so it's dropped out of the population. Just to sort of explore this a little bit more, I started the same exact simulation as I started here, but this time I basically started it out from this point here, where I started out with 50% of people are resistant and 50% of people are susceptible, and I've just introduced one person that's infected. So I introduced one person that's infected here. And what we see is that the dynamics are different in that the virus just sort of drops out of the population. The number of infected people just drops down, it's gone. And so we do find that some people got infected and have recovered. So there's some drop in the susceptible and some increase in the resistant population, but it was really, really very minor. Very few people got sick. And the important point is the virus rapidly left the population. So this was a population that was actually at a population level resistant to this virus. It came, it was introduced by a single person, but because people were social distancing and because 50% of the population was already resistant, the virus could not take hold in that population. This phenomenon is something that we called herd immunity. And so you might have heard about this in the news, and I started out the lecture in talking about herd immunity. This is how it works. Basically, there are so many resistant people, they provide this speed bump and they slow down the pathogen, and so the pathogen just can't make its way to finding a susceptible person before it's just lost. Here is a really nice diagram that I'm not going to walk through step by step. The idea is that if you have a population with lots of susceptible people and you have a few people that have the pathogen, then it can rapidly spread through the population. And then if you have a population that has some susceptible people and some infected people, but most people are immunized or recovered, then you can actually get a situation where that pathogen really has a hard time spreading to any of the susceptible people and it just drops out of the population. And so I'm switching the word that I'm using here from recovered to immunized. So this principle that plays out for natural recovery can also play out if we have a vaccine and we immunize people from this pathogen. And so if we do get a vaccine and give it to lots of people as soon as possible, then we might be able to artificially create herd immunity. We don't have to wait around for all those people to be recovered. We can cause that population to increase ourselves artificially with a vaccine. And so a lot of people, I'm going to wade into a kind of contentious debate here. A lot of people are, called anti-vaxxers or whatever. They do not want people to receive vaccines, and there's a lot of pushback on that group of people. One, because the science doesn't support that vaccines have such a deleterious effect on people, so many side effects as these scam scientists have claimed. So the science is bad, but also because it actually puts our population at risk. And so if you have a population and you have the majority of your people immunized, then diseases can't spread in the population, even if there's a few individuals in that population that are sensitive. Now, remember, it'd be great if everybody could get vaccines, but you can't get vaccines if you are, say, immunocompromised. Vaccines work by leveraging your immune response to deal with the pathogen, but if you're immunocompromised, then you won't have that response, and so the vaccine won't be effective. I personally can't take influenza vaccines because I had that autoimmune response, that affected my neurons, caused that Guillain-Barré syndrome, where I was out for that month as a senior in college, in the ICU, and then out from actually that whole semester recovering. So very traumatic, and it means that if I can't get a flu vaccine because I got that autoimmune response from getting the flu. And so a vaccine could trigger the same kind of chemical or biological cascades that lead to that autoimmune syndrome and me possibly being paralyzed and blind and unable to breathe and all that terrible shit again. So I can't get the flu vaccine. And so I tell everybody around me, please get the seasonal flu vaccine. You guys are providing a buffer so that I don't get the flu. I can't get the vaccine myself, and I also don't want to get the flu because it could trigger this autoimmune response again. So it is really important that we think not just about ourselves, but collectively when we're thinking about vaccines. And I think it's incredibly self-centered and misguided that people have these anti-vaccination protests and so forth. Okay, but this phenomenon leads to this idea of herd immunity. And I just want to circle back to one figure that we saw in an earlier lecture when I was talking about what should we expect over the next couple of years. When would we naturally become resistant or recovered from SARS-CoV-2 and the COVID-19 pandemic? How should we monitor the spread of the disease, and how should we pulse in social distancing versus letting off social distancing and so forth? And we had 4 different predictions, and this was the 4th prediction where there was a seasonal effect, and we had periodic social distancing, and we also increased the level of our hospital beds we doubled them to 100 in this unit, prevalence per 10K. And so don't worry about all the details here, but if you want to go back to that earlier lecture, we talked a lot about this, and I just kind of glossed over this. And what this is telling us is this is the number of the R's. So this axis here is actually the number of R's over time. And we see that it's steadily increasing through time. And then there is this other line here at 50%. And that line there is the threshold that these epidemiologists have determined mathematically is the threshold that if we get to 50% recovered, then the disease is going to have a hard time spreading within the United States, and that it's going to eventually drop out of the population. So what we see here, why the disease actually drops out of the population, is that we're getting near this threshold of herd immunity, and eventually we reach that threshold, and then there's no hope for SARS-CoV-2. So this modeling here is much like is a more advanced version of what we're going over today. And I just wanted to circle back to this idea of herd immunity, and that's what that threshold is right there, herd immunity. Okay, so now I want to get to that variable called R naught or RO. And R naught it's called reproductive ratio. It is this variable that tells us whether or not a disease is likely to spread or if it's just going to go away. We don't have to worry about it as much. And R naught is a composite of the variables that we've seen in the SIR model. And so this is something that is derived from that SIR model. It is based on this beta, so the transmissibility of the disease, and then it is inversely related to the death rate of the population that is being infected, the virulence of the disease, and the recovery rate of the disease. So let me just sort of go over the mechanics of how this works first. So this would make sense if you're looking at this. So whether or not a disease spreads is going to be determined by, how fast it can transmit from one person to another person. It is going to be negatively related to how fast that person recovers. So that makes sense. If you have a really fast rate, so it takes very few days for a person to recover, then that means that that person can't spread the disease to as many other people, and so it's going to reduce the ability for that disease to spread. This virulence here, or the amount of death that's being caused by the pathogen itself, this negatively impacts the spread of the virus in that if the virus or the pathogen kills off a person, kills off its host, then that virus is going to sink with the ship, and it's not going to be able to spread to more people. So I think often people associate virulence and mortality with viruses, and you would get the intuition that that's good for viruses to kill off their host because we have this association. However, it's actually bad for the virus. It wants to maintain its host in a position where the host can spread the virus to other susceptible hosts. And so it's not good for a virus to be virulent. And this is just if you have a high rate of natural mortality in the population, then that's going to decrease the number of infected people that can spread the virus as well. So that's you don't have to worry about that too much, but that is in the denominator in this equation. Okay. So the greater the infection rate, the lower the virulence, and the slower the recovery rate is, the more the pathogen will spread. So you put all of these different rates together and you derive R naught and you get a number, okay? R naught itself is not a rate. It is a number. It's a flat number for the number of new people that get infected per person that is infected, okay? So I didn't say that clearly. But basically, let's sort of walk through this picture here. So we have two different scenarios, two different R naughts. In the first scenario, we have a population of all susceptible people, and we have one infected person. And then during the course of the period in which this person is infected, if the virus or the pathogen has an R naught of 1, that means that it will cause one of these susceptible people to become infected. So it's basically just maintaining a steady spread of the virus. It's not increasing, it's not decreasing. Whereas if you have an R naught of 5, that means during the course of this infection, this person is going to transmit the disease to 5 other people. So 1, 2, 3, 4, 5. So now this is actually where you have this exponential expansion of the disease, because now during the course of the infection, each one of these infected people will yield 5 new people. And so the way that R naught works is that if you have an R naught that is less than 1, then the disease is going to be lost from the population. If you have an R naught that is greater than 1, then the disease is going to spread through the population, and it's going to increase in numbers until there's some kind of intervention or the population gets a lot of recovered people. So that is what the R naught number means. It's the number of new individuals that get infected from a single infected person. So human diseases vary a lot in their R naught values. And so you can take a look at this table. You certainly do not have to memorize it for the actual exam. But it shows you that there's a lot of different diseases over here, and they have different levels of, or they strike sort of different levels of fear in us. So I'm very afraid of Ebola, of course. I'm less afraid of influenza. I'm very afraid of HIV, and so forth. But that sort of intuition does not actually translate well to the R naught. And so R naught, it's this thing that's determined by lots of different variables. It's not just determined by how infectious a virus is. It's also combined with how virulent a virus is. And so you can look at this table, and there's actually some viruses that you would have thought might have had a higher R naught, or you can make sort of comparisons between viruses, and some of them, our intuitions about how viruses spread and how viruses work don't line up with the actual R naught value. So you have to always remember that R naught is this composite of beta, virulence, and recovery rate. And so, for instance, let's just sort of compare and contrast some of these viruses. So actually, HIV, normal, so influenza, and Ebola, they're actually in the spectrum of viruses. They have very similar R naughts, but they seem very different. So with HIV, it's actually, it does cause mortality, but it takes a very long time to cause that mortality. And so its virulence is kind of intermediate because of that reason. Its beta is not that high because it actually takes transfer of bodily fluids, but its recovery rate is extremely low. People don't recover from HIV. And so because of that, that is what inflates its R naught and allows it to spread and cause the worldwide pandemic that we've seen. Influenza, on the other hand, people recover from it, has a really relatively low virulence, and it has a relatively high beta because it can be transmitted through the air, through respiratory droplets. And so that's what sort of gives it an equivalent R naught with Ebola and near HIV/AIDS. Ebola, we're very terrified of Ebola, but it has a high virulence. And so even though it's pretty infectious and people don't recover from it, so very slow rate here, it has a really high virulence. And so basically it kind of burns itself out. It wipes out its host, and so it can't spread as well. And so what you can do is sort of walk through these different examples and compare and contrast and see sort of how one might vary in beta and another one might vary in virulence, and how that plays out in shaping the value of R naught. Okay, so here's just a question to take a break and think. And we've already gone over this, but this is an example of a type of multiple choice question that I would give on the exam. And this is if you increase the virulence of disease, you'll actually produce a lower R naught. Ebola is actually not as able to spread as it could be if it wasn't so harmful to us, if hosts weren't so sick when they got it. So since virulence is in the denominator of R naught, you may expect that pathogens should evolve to reduce their negative impact on their host, to reduce their virulence. If there is a way for them to persist in the host without causing mortality, then that would be good for the virus. If there was a mutation that had that effect, then that mutation would be favored and would spread in the population and create a less harmful pathogen to us. And there is some evidence that pathogens do evolve to be less virulent over time. This is not a hard, fast rule, but there is evidence that this happens. And so we'll go over this more, and you actually look at the data when we have the HIV lecture. But here, this is just a paper where people examined data and asked this question whether or not HIV is evolving to be less virulent over time. So HIV is this pandemic that happened and is this persistent infectious agent in the human population. And so there is opportunity for that virus now to adapt in ways to better spread in humans. And one of the ways that it appears to be adapting is it's reducing its virulence so that it can spread to more people. And so the evidence, and we'll talk about this later, is that there is a subtype of HIV-1 called subtype C, which seems to be becoming more and more dominant through time in human populations, shifting the overall genetics of the virus and causing its evolution. And it seems related to the fact that this subtype is less virulent and can persist for longer in patients and spread to more people. So then that observation leads us to the question of, if virulence is bad and evolution can push viruses to be less virulent, then why do we still have viruses in humans and viruses that have been in humans for many, many generations? Why do some viruses maintain a high level of morbidity and mortality? Morbidity is just a high level of causing disease and sickness. Mortality is death caused by disease. So what are we kind of missing here? And so the thing that we're missing is that the characteristics of viruses that allow them to spread often also cause mortality. And so beta and virulence are kind of stuck together. This can be understood as a virus, in order to spread, it has to produce a lot of viral particles. Well, when it produces a lot of those viral particles, those particles can spread to other cells within the same host, causing even more damage to that host, and so causing that host to possibly even die from that damage. But because they produce all of those viral particles, they also have an increased beta in that those particles can sort of leave that host and spread to another host, susceptible host, and spread the disease. And so if you just think in terms of the number of particles being produced, the traits that increase the number of particles, so increase the ability to spread, are also the traits that are going to increase the virulence of the pathogen. And so these are locked, or often are locked together, so that if you increase beta, you'll also increase the virulence of the virus. And so evolution is stuck, and natural selection is stuck dealing with this thing that we call an evolutionary trade-off, where it maximizes its ability to spread. It maximizes R naught by balancing the beneficial effects of traits that improve beta without paying too much of a price in how they shape virulence. So the nature of this trade-off determines whether or not the pathogen will evolve to be more virulent or evolve to be less virulent. So let's walk through how that actually plays out. Okay, so first thing is, there is data that suggests that viruses do show this trade-off. And so this is data from just experimental data that's really straightforward and nice work from this Messinger paper in Jim Bull's lab. But the idea here is that as you increase the transmission rate, that's very good for the virus. So this is increasing beta. But as you do that, then because the traits are correlated with each other, you get an increase of virulence, which is bad for the host and also bad for the virus. So that's why it's a trade-off. This is good, but it causes this, which is bad. That's the nature of a trade-off. I should have explained what these points are. these are different genotypes of a virus, and they have different transmission rates, and those different transmission rates also cause differences in virulence. And so natural selection can be acting on these individuals so that maybe it'll promote this individual because it can spread very quickly, but it's going to have the trade-off, the consequence of also have a really high rate of virulence. And so it's not clear-cut whether this individual would actually be better able to spread than this individual down here that sure has diminished transmission rate, but also is not very deadly to its host, and so it can transmit even more. So that's how a trade-off works, and this is just an example of the mechanism underlying a trade-off that we already went over, based on increased number of particles increases transmission rate, but also increases the virulence. So the question is, given this information, can we predict whether or not natural selection will push the population to have more of these highly transmissible, highly variant types, or will natural selection push the population so it favors these types that are more benign? Yes, they can't spread as quickly, but they're also not killing off their host and giving the virus more opportunity, more time to spread from one host to the other host. And so what information you need to know is basically how steep is this trade-off curve? And so if you have a really, really steep trade-off curve here, so these are individual Ebola genotypes. Now this is hypothetical data. These are individual Ebola genotypes. And when you fit a line to these characteristics, infectious rate and virulence, you see that it has a very steep slope. And in this scenario, and given this trade-off, you would predict that this one would be the most fit, that it would have an enormously high rate of infection, high beta. It would have an increased virulence, but you've gained so much beta that increase in virulence doesn't matter. And so the way that you can sort of think about this trade-off and think about this equation is that when you have a really steep line, you are increasing the y, so increasing the beta by a lot, and you're only increasing the virulence by a little. And so natural selection is going to favor the ones that really increase the beta because there's not much of a cost to doing that. And so your R naught is going to be maximized by pushing this trade-off all the way to its edge. In the sort of an opposite case, and again, this is just hypothetical data, but say we have a bunch of genotypes of mumps that vary in their infection rate and their virulence. There's a correlation. That means there's a trade-off. But now the slope of this line is much shallower. What that means is that there's very little Y gain, very little gain in beta, given the enormous gain that's happening in virulence. And so as you're moving out here, you're gaining lots of virulence for a little bit of beta. And so actually natural selection would push you down this curve. So it's going to push you down to reduce your virulence and to reduce your beta. So the benefit, you're gaining most of the benefit by reducing your virulence, and you're going to reduce it a ton. So that's this distance here per unit of beta that you're reducing. And so the virus is gaining a lot here compared to its kin. It is gaining the ability to spread because it's not killing off its host. Yes, it's not as infectious, but it's better able to spread. This selection would maximize the R naught of this virus by favoring these types that are more benign. So the summary is there's different theories that give different explanations for why virulence increases or decreases over time in pathogens. But this is a really dominant idea, is that the reason why different pathogens go on a different course of evolution, become more pathogenic or less pathogenic, is based on the nature of this trade-off, and that there might be characteristics of the traits of Ebola that give it this really steep trade-off curve, and there's characteristics of traits in mumps that give it a really shallow trade-off curve, And so the steepness of this curve is determining whether or not selection favors the really virulent type or the really benign type. So I put together an extra slide. The slide goes over what I just talked about, but in more quantitative detail. I wanted to use that equation, match the equation with different points along those trade-off curves to show you really how the steepness of the trade-off curve will determine whether or not natural selection selects for viruses that have higher transmissibility and higher virulence, or viruses that have lower transmissibility and lower virulence. So there's a lot going on this slide, but let me just sort of walk you through this example. In both, we have two different scenarios, two different trade-off curves. And in both scenarios, we're going to simplify things by making the death rate of the population 0. So this is that natural death rate, not the death rate due to the disease. That's virulence. That's V here. So the death rate is 0, and the recovery rate is also 0. And so that just sort of simplifies things so that the R naught ratio is dependent on just the beta and the virulence. And so here we have two different trade-off curves. And in this scenario, we don't have sort of a whole cloud of genetic variants. We just have two genetic variants, one at one end of the trade-off curve. So for example, down here, and one at the other end of the trade-off curve. Here are our two genetic variants on this side, one that has low transmissibility and low virulence, and one that has higher transmissibility and very high virulence. So these are two genetically distinct variants of the same virus, as they are spreading, natural selection is promoting one over the other, and we can use this R naught equation to predict which one is more likely to spread, and therefore which one is more adaptive. So in this scenario, let's start out here where we have a point at 0.2. So that's just lining up down here on the x-axis, that's for virulence, and 0.9, that's lining up here for transmissibility. And when we calculate the R naught, 0.9's in the numerator, 0.2 is in the denominator, and that gives you a value of 4.5. So that's a very high R naught. This virus is highly likely to spread. Whereas we look at its genetic relative, and its point is 0.1 and 0.1. And so obviously 0.1 divided by 0.1 is just 1. And so that's an R naught where maybe this thing could spread, maybe it wouldn't, but certainly in the face of competition with its more virulent and more transmissible relative, that relative is going to take over and do a lot better. So under this scenario, you get selection for this genotype, and natural selection will push the evolution of this virus to being more dangerous for us. Here's another scenario where we actually have selection favoring the exact opposite trajectory, where the virus should become more and more benign and less harmful over time. And so here, when we just run through the same calculations, now this point here is 0.9, 0.2. So just flipping the x and the y to give now a very shallow slope. What we have there is when we do the calculation, we now get 0.22. And of course, this is the exact same point as this one. And so the calculation is an R naught of 1. So under this scenario, this one is going to decline in abundance over time. This one's going to stay about the same. And so certainly, even though this one might not be really able to spread widely, it's going to do a lot better than this guy. And so natural selection is going to favor genotypes on this end of the spectrum and promote a shift in the virulence of the virus or other pathogen to being more and more benign. So I hope that helps you guys seeing the actual raw numbers, how you make these calculations, and how you can actually determine quantitatively why the direction of selection changes given the characteristics of these trade-off curves. Okay, so just to summarize, and we have a couple more slides, But to summarize, we can use these SIR models to make predictions about diseases, and they're relatively simple models, given how complex the natural world is, for them to be able to actually make pretty good predictions. That's good. Whether or not a disease spreads is determined by this R naught value, and the SIR model can be used, and the R naught can be used to help us understand how virulence evolves, and actually make a prediction for whether or not a pathogen, if we have that trade-off curve, whether or not a pathogen will evolve to be more or less virulent. So of course, remember, go over this model and remember how it works and how this SIR model translates into this R naught and how to interpret the value of R naught. And one last thing that I want to plug is one of my colleagues and really close friends, Luis Simon, has been playing around with these types of models, but he is making online simulators that are more complex than the one that I talked about. He's actually incorporating spatial structure into his model. So that was one of the features that I pointed out, is a simplifying assumption of the SIR models. So Luis has complexified it so that you could better understand how pathogens spread during pandemics. And when you have spatial structure, so when you have different countries or different regions that the pathogen is spreading to, or if you have a local community where you have people that are sheltering in place or varying levels of sheltering in place, his online simulator helps you build an intuition for how that spatial structure plays out and how it actually slows down the transmission of pathogens. And so this is just outputs from his model showing the SIR dynamics, and he's also added this exposed category, so you can read about that. Here's the spatial structure. People tend to stay within their homes or regions and not spread between them. And then this is a network of transmission that is being established during the simulations. You can watch that grow just as we watched the transmission map across the globe grow in the nextstrain.org. Okay. So thank you guys. I hope you enjoyed that lecture. I hope that you have a better intuition for how epidemiologists are making these predictions using SIR models and other types of models like that. And you have a better understanding for how viruses are trapped in this dilemma to increase their infectivity but reduce their virulence, and how the nature of the trade-off between those can influence whether or not a virus will evolve to be highly pathogenic or benign. Thank you guys very much. I'll see you again on Thursday, and take care, social distance. Cheers.